Hi everybody, welcome to my YouTube channel. My name is Aaron and I'm gonna try and bring some new concepts talking about glycolysis, which is key in the formation of biomedical studies, biology and biochemistry. But sometimes students tend not to understand clearly what it's all about, and it can be overcomplicated when it's actually not that complicated. So I'm gonna find a way to make it easier for you to understand it. And hopefully at the end of this presentation, you're going to be able to know what glycolysis is about, what you're gonna get from it, what you need in order to do it, why you need to do it, and why you need to understand it. Okay, so let's start with some important questions that we need to review. Whenever you have a pathway, a biochemical pathway, or a metabolic pathway, you need to ask yourself these four questions, which are: where does this reaction take place? And I don't mean the organ tissue. I mean where in the cell. So does it take place in the nucleus? Does it take place in the cytoplasm? Does it take place in the mitochondrion? So this is what you need to ask yourself. Second question, what are the reagents? So basically, what are the ingredients that you need in order to perform this chemical reaction? What are the products? So what are the final products that you're going to get, or what you're going to get from this chemical reaction? And what are the rate-limiting enzymes? Because sometimes chemical reactions, chemical pathways or metabolic pathways tend to have like 10 chemical reactions, chain reactions, and they become overly complicated. But you just need to understand the rate-limiting enzymes, which are 3, sometimes 4 maybe. And you need to understand that they are at the beginning of a chemical reaction or in a crossway, so basically in a crossroad, or at the ending of a chemical reaction, or at the ending of a pathway. Okay, so once we learn those things, you're going to be able to say that you do understand the chemical pathway. Okay, so let's start with, in this case, we are going to talk about glycolysis. And glycolysis is basically the initial stage of glucose metabolism. So glucose is going to become pyruvate, and it's going to generate ATP, which is energy, and reduced NAD or NADH, which is reducting power. The entire pathway is carried by 10 enzymes in total. It's an anaerobic process, and it takes place in the cytosol, which is the fluid part of the cytoplasm. And it's basically the same in every cell. It doesn't have many variations, and we don't actually need oxygen in order to perform it, which is why I insist that this is an anaerobic process. The purpose of glycolysis is to provide quick energy and intermediates for other pathways. For quick energy, which is ATP, intermediates for other pathways, which are NADH, or, well, in my first language, we would say reduced or reduced NAD. General equation, we need glucose, 2 molecules of ATP, we need actually 4 molecules of ADP, 4, not 2, and 2 molecules of inorganic phosphate and reduced NAD. Sorry, this is oxidated NAD. And what are we going to get? So which are the products? 2 pyruvate, 4 ATP, 2 reduced NAD, 2 protons, and 2 molecules of water. There is something going on here that as you can see, we have 4 ATP and 2 ATP in here. So mathematically, these 2 can be cancelled out by 2 in here, which is why the need yield, so the need gains, we're going to get 2 ATP. At the ending of the process, we're going to get a need yield of 2 ATP. This is going to become apparent later in in the process. Phases of glycolysis. So we have two phases. The first one is the energy investment phase, in which glucose is activated and broken down. So we need two molecules of ATP in order to phosphorylate the glucose and then break it down into two molecules of 3 carbons. Glucose has 6. And the second phase is the energy payoff phase, in which we are going to get our return. So we are going to get our ATP's worth from the process. What do we get for ATP? To reduce oxidated NAD to pyruvate by every molecule of glucose. Remember, one molecule of glucose has 6 carbons, and each pyruvate has 2. Okay, the net yield is going to be 2 ATP, 2 pyruvate, and 2 NAD. Okay, so now we're going to talk about the energy investment phase, in which we need 2 molecules of ATP in order to activate 1 molecule of glucose and then break it down. It's important that you understand that regulatable enzymes are going to be shown in red, and those are the ones that you actually do need to understand and you do need to learn. So out of those 10 enzymes that we're going to study, you will only need to actually learn 3 of them. So this makes the learning process easier. And let's see what we can get. Okay, so we have glucose. Once the molecule of glucose enters the cell, the first chemical reaction is going to be performed by exokinase or hexokinase, which is hexokinase 4 or hexokinase 6. Hexokinase 6 is also named as glucokinase, which is in the liver, and hexokinase 4 is going to take place in every other tissue. So look, we are going to invest 1 molecule of ATP. This molecule is going to become ATP, and the extra phosphate, so this is adenosine triphosphate, and now it's adenosine diphosphate because the third phosphate is here now. So glucose became actually glucose 6-phosphate, okay? And this is the first enzyme that we do need to understand, or we do need to memorize, or we do need to learn, okay? Then we have the second enzyme, which is phosphoglucose isomerase, and this is going to isomerize this glucose into fructose. This is going to become apparent in here. Of course, this is not exactly what's happening, but my explanation is being very graphical. So what I need you to understand is that this molecule I'm going to put, in order to show the difference and that this is isomerization, I'm going to put this phosphate in here, so it becomes more obvious for you. Look at what is going to happen. So now we have fructose 6-phosphate. And why? Look, we still have 6 carbons. It's still a carbohydrate, but now this is no longer glucose. This is fructose, which is an isomer of glucose. Okay? Which is what I'm trying to show here. Okay, now the second enzyme that is regulatable is phosphofructokinase, or PFK1. And what it's going to do is going to add an extra phosphate into this fructose 6-phosphate. Let's have a look. Once again, ATP is invested, and this ATP becomes ADP, and this extra phosphate is now here. So look, now we have fructose 1,6-biphosphate. Okay, so now we have 1 molecule of 6 carbons, and it's phosphorylized in 2 places, 1 and 2. Okay, so remember, 1 and 2 key enzymes that you do need to understand. This is the point of no return. So after this reaction, this molecule is for sure going to become is for sure going to take the pathway into glycolysis. So there is no going back after this. This is the most important regulatory enzyme that we have. Okay, so the next enzyme, which is called an aldolase, what it's going to do is cut this molecule into two halves. So the first half is going to be dihydroxyacetone phosphate, and the second half is glyceraldehyde 3-phosphate. I'm going to concentrate, or I'm going to focus in this one, because look at what is going to happen. Okay, so I wanted to emphasize that, and look at what is going to happen. So I now have another enzyme, which is a triose-phosphate isomerase. Once again, an isomerase. And what it's going to do is going to bring this phosphate from here into here. And now we do have 1 and 2 glyceraldehyde 3-phosphate. Okay. So we have 2 of the same. And once we get here, this is the ending of the first phase of the glycolysis process. So this is the ending of the inversion phase. The second phase is the energy payoff, and basically in this phase is when we get our money's worth, or our ATP's worth. Okay, so now we're going to get our yield in ATP. Remember, we have 2 glyceraldehyde triphosphate. Okay, so we have 2. So from here on, every chemical reaction must be considered as twice. So whenever you see something, is going to happen twice. Okay, because look, let me go back. Once and twice. So every chemical reaction is going to happen twice, once and twice. Our brute yield is going to be 4 ATP molecules per glucose, and the purpose is to obtain energy in form of ATP and reducting power in the form of NADH. Okay. Once again, regulatory enzymes will be shown in red. Okay, so here we go. Once again, glyceraldehyde triphosphate. Wow. Due to this enzyme, which is called glyceraldehyde 3-phosphate dehydrogenase, or GAPDH, maybe it's easier if you learn this acronym. Now look, NAD, which is reduced, is going to, which is oxidated, is going to be reduced into NADH and protons, 1 proton. Okay, and in here we have 1 extra phosphate that was added into our molecule, and now we have glyceraldehyde 1,3-biphosphate, or 1,3-BPG. Okay, look at what is going to happen next. Phosphoglycerate kinase, what is going to happen is going to remove one of these phosphates and is going to give it into 1 molecule of ADP, so it's going to become a molecule of ATP. And this is our first yield. We now have 1 ATP. Actually 2, remember this is happening twice. So we have our first 2 ATP molecules. And what do we get? 3-phosphoglycerate. Okay. Now we get another enzyme, which is phosphoglycerate mutase, which is going to bring this phosphate from here into here. Have a look. Okay, so carbon 3, now it's in the second carbon. Now it's phosphoglycerate 2-phosphoglycerate. And I'm going to emphasize here, don't get scared, I'm just going to bring it into here because I ran out of space. And look at what is going to happen. This enzyme, which is called enolase, is going to remove water. So this is how we generate water in the reaction. 2 molecules of water. And now our molecule is called phosphoenol pyruvate. I changed the color because if I didn't, it would look the same, as 2-phosphoglycerate, and I wanted to emphasize that this is now phosphoenol pyruvate. And since I'm not using chemical denominations or chemical bondings, I'm just using graphics. It makes better sense that I just change the color. Now we have our third chemical reaction, our third regulatable enzyme, which is pyruvate kinase. And what is going to happen is this phosphate is going to be removed from here, and it's going to deliver it into another ADP molecule, so that this molecule is going to become an ATP. Have a look. ADP, ATP. So 2 ATP and 2 ATP molecules. Now we have 4 ATP molecules. And this is pyruvate. So this is our final product in here. So in summary, or to summarize, remember, and now we are actually answering the questions that we asked ourselves at the beginning of this presentation. The reagents: 1 molecule of glucose, 2 NAD oxidized, 2 molecules of ATP, 4 molecules of AGP plus inorganic phosphate, which is this. And the products, we get 2 pyruvates, 1, 2 here, 2 NADH, 2 protons here, 4 ATP in brood, 2 in here and 2 in here. Remember that is happening twice. And out of those 2 are net yield because we used the other 2 in our investing phase. And 2 molecules of water, which are here. So now you have a summary of what we actually get. Okay, and glycolysis can also, so up until now we finished the process of glycolysis, but I want to explain to you what is going to happen after here. So up until now, you already know glycolysis. The next step is that you understand what is going to happen basically to these things. Mostly to pyruvate and NADH. Okay, so this is going to happen in 2 contexts. Okay, so in an anaerobic context, this NADH is reoxidized into NAD oxidized, and that is by conversion of pyruvate into lactate in humans, or ethanol in plus carbon dioxide in yeasts. In here, no extra ATP is gained, okay? And in the aerobic context, this reduced NADH is going to be entering the mitochondrion, and more specifically the mitochondrial electron transport change. And in here, this is going to yield more ATP. So in an anaerobic context, in an anaerobic phase, this NADH is not going to give us more ATP, but if we have presence of oxygen, we are going to get more ATP. And look, this is how. In glycolysis, anaerobic glycolysis, this NADH is reoxidized, as we were talking about. Look, this pyruvate, because of this enzyme, which is lactate dehydrogenase, is going to become lactate. Lactate is the chemical that makes our muscles sore when we go to the gym. So this is an acid, actually. So NADH is reduced into reduced NAD, and we have lactate. Since this NADH didn't enter the mitochondrion, then we do not get extra energy. And this is lactate fermentation. This is what happens. This is what happens in humans. And this is alcoholic fermentation. In alcoholic fermentation, this pyruvate, once again, we got it from glycolysis. Because of this enzyme, which is pyruvate decarboxylase, is going to become acetaldehyde. And of course, this is going to release carbon dioxide. Okay, and this acetaldehyde is going to be is going to be becoming ethanol because of this enzyme, which is called alcohol dehydrogenase. Okay, in here, this NADH, which is not reduced, is going to reoxidize. And when this reoxidizes, okay, of course, since this is reoxidized, this will not enter the mitochondrion, so no extra energy will be produced once again. And well, this is ethanol. Once again, this is what happens in yeasts, okay? And alcoholic fermentation is not particularly effective in aerobic environments, but is really effective in anaerobic environments. So in the in deficit of oxygen, these yeasts are going to thrive, okay? And this is how we can get alcohol, for example. Okay, and now take a look at what happens in an aerobic context, okay? So this reduced NADH is going to enter the mitochondrion, okay? And when it enters the mitochondrion, it's going to participate in the electron transport chain. So here, look, NADH, this is the mitochondrial matrix, okay? And this is the intramembrane space. Of course, if we go here, this is going to be the other mitochondrial membrane. Remember that the mitochondria has two membranes, one inner, which is this one, and one outer, which we do not see here. But basically, this NADH, this reduced NADH, is going to pump this proton into the intramembrane space, okay? And it's going to, we do not see it here, but these protons are going to come back later in the ATP synthase, and we are going to get extra ATP. So this is what happens in a context where there is presence of oxygen. This is how the extra ATP that we're talking about is generated. Okay, so now that you know the two contexts of what happens, we are going to talk about why the regulatory enzymes are important. Basically, because they are rate-limiting enzymes, and they catalyze non-reversible chemical reactions. So they are going to be under allosteric or hormonal control, and they are going to control the flow of the pathway. Okay, so if we have a lot of ATP, it doesn't make a lot of sense that we go through glycolysis. But if we do not have a lot of ATP, it makes a lot of sense that we go through glycolysis, and this is why these enzymes are important. We talked about 3, and in here you see 4. But the thing is that this is basically the same enzyme, but in 2 different tissues. So exokinase 6 is present in peripheral tissues. So exokinase 6 is present in peripheral tissues. When I say peripheral, I mean anything but the liver and the pancreas. And hexokinase 4 or glucokinase is present in the liver and the pancreas. But look, they have some different characteristics, but they are going to be performing the same chemical reaction, which is glucose is phosphorylated into glucose 6-phosphate. Same chemical reaction, okay? Characteristics. Hexokinase 6 is going to be inhibited by its own product. And this is important because if it has a lot of the same product, and this is a peripheral tissue, that means that it's going to like put on a traffic light, or it's going to brake. It's going to stop the chemical reaction. Whereas glucokinase or hexokinase 4 is present in the liver and in the pancreas, and it's induced by insulin, and it's not inhibited by glucose 6-phosphate. And it makes a lot of sense because the organ that is in charge of regulating glucose is the liver. Students or people who are learning this tend to think that the organ in charge of regulating glucose is the pancreas because of the production of insulin. But the thing is, the pancreas is going to remove that extra glucose from the bloodstream, yes, but the one who is going to process it is actually the liver. Okay, so the liver is the one that regulates the glucose levels. Okay, so if the liver is always working with glucose, it makes a lot of sense that it's not inhibited by glucose 6-phosphate. And this is the reason why it's not inhibited by its own product. Okay, and also it has a lower, we're going to see it later, but it has a lower affinity. Glucokinase has a lower affinity with glucose, and it's very important to understand why. Phosphofructokinase, or PFK1, turns fructose 6-phosphate into fructose 1,6-biphosphate. This is the main regulator, and this is as we were talking before. This is the point of no return. This means that from here on, not here, from here on, the only way that we are going to go is through glycolysis. Okay, and the last enzyme that can be regulated is pyruvate kinase, which turns phosphoenol pyruvate into pyruvate, and it's activated or inhibited according to energetic needs of the cell itself. So if the cell needs more energy, then the enzyme is going to be activated. If the cell doesn't need more energy, then the chemical reaction is going to be stopped. The enzyme is going to be inhibited. Okay, so here we have a summary of the three enzymes that can be that are regulatable. We have hexokinase 6, which is present in peripheral tissue and is inhibited by glucose 6-phosphate, so negative feedback. We also have hexokinase 4, which is glucokinase, which is present in liver and pancreas. It's important to understand that this enzyme has a lower affinity for glucose. And this is really important because, for example, let's say that you just ate. Okay, if you just ate, this is when you have a greater amount of glucose in your blood, in your bloodstream. And then, of course, that glucose is going to enter your liver. And this enzyme is actually really good or works really good in higher concentrations of glucose, because let's say that you just had dinner or lunch or whatever, your glucose levels are going to be high, and you need to regulate that amount of glucose. Okay, so this is how this enzyme works better. And now let's consider the opposite. Let's say that you're fasting. So if you're fasting, your glucose levels are going to be low, and whatever amount of glucose, or not low, but they're not going to be high actually. So you need that glucose in order to move your muscles. You need that for an energy source for the brain. Okay, so you do not need to use it in the liver. You need to use that glucose, whatever amount of glucose you have, in other tissues. And actually, the liver needs to be releasing glucose into the bloodstream. So this is when you go through glycogenolysis and neoglucogenesis. So you activate other processes that increase the level of glucose in your bloodstream, not lower them. Okay, so this allows the liver to phosphorylate glucose only when the glucose is abundant. So when you have a lot of glucose. Second enzyme, phosphofructokinase. This is an E. This came from my first language. Sorry for that. Or PFK1. This is the most important regulatable enzyme. Can be activated because of or by AMP or ADP, which are lower energy indicators. AMP is adenosine monophosphate. ADP is adenosine diphosphate. Fructose 2,6-biphosphate, which is an hepatic activator, and it's activated by insulin. And it's inhibited the opposite when you have a lot of energy, which is ATP, or which is a high energy indicator, or citrate, which is also a high energy indicator, because this citrate is going to enter the cycle of Krebs. And from the cycle of Krebs, we get a lot of ATP also. So why to go through glycolysis if we have citrate that is going to give us like 30 molecules of ATP? And pyruvate kinase, which is the third regulatable enzyme, can be activated activated by fructose 1,6-biphosphate and can be inhibited by ATP, alanine, which once again are high energy indicators. And in the liver is regulated by phosphorylation. So it's inactive at fasting and it's active at postprandial state. Once again, why to activate glycolysis when you are fasting? You actually need to release glucose from your liver, not use it. Release glucose from your liver. How? From glycogenolysis or from neoglucogenesis, not glycolysis. Okay. And it's very active in postprandial state. So basically, postprandial state is when you just ate. Okay. I really hope this was helpful. I tried I tried my best to make myself understood even with my accent, and I hope first to become better at this, and second that you're able to understand the things that I was talking about, and hopefully I will see you again in another video. If you have any suggestions or any questions, the comment section is open for you. And okay, hopefully I will see you later. Bye, and thank you for your attention.